Hey guys, we're going to look at two examples from your notes packet that are hopefully going to shore up your understanding of torque and moments of inertia. So if you don't have your notes packet out, I would go ahead and get that out at this time. The first example we're looking at is example 3. And so if you read the text there, you can see that it's describing a meter stick, which is pivoting about the 10 centimeter mark. Presumably that would mean like a hole is drilled through it there, something like that. And then a 1 kilogram mass is hung at the 0 mark. Whoops, missed the end. Let's try that again. Oh, still missed. My fingers are too fat for this. All right, so there we're going to hang a 1 kilogram object off of there. And you could kind of guess that if you set things up this way, what would probably tend to happen is the far end would twist up like that, and this end would, of course, twist downish, right? Based on the fact that the 1 kilogram mass being hung there is going to produce a torque because it exerts a force not directly at the pivot point, right? So we had that equation from class, sum of torques, sorry, wrong one, torque equals F cross R. So the torque that the 1 kilogram weight would be producing would be equal to its weight times the distance that it is from that pivot point. Or at least it would in the orientation that's shown, right? Remember, there's also this fact that this equation really is FR sine theta. And so the angle between the radial vector, which is that, and the force vector is going to affect exactly what the torque is. That should say sine theta. Okay, so in the position shown, the torque produced by the hanging weight would be mg times r, and in this case r is 10 centimeters, so 0.1 meters. All right, fine. So what question A is asking, though, is not like what amount of torque does that hanging weight produce, but what would we have to hang all the way at the other end in order to make things exactly balance out, right? If we hang something else at the other end, you can conceptually understand that it ought to be possible to make this meter stick balance in this picture. Okay, so what we're dealing with here that we didn't discuss in class is the idea that you can have more than one torque acting on an object, and therefore you can talk about the sum of the torques. All right, now, the sum of the torques is going to be equal to I alpha, and that's actually analogous to F equals ma. I'm sure everybody remembers good old F equals ma from back in the day, a few units ago. A force produces a linear acceleration. A torque produces an angular acceleration. So therefore, our torque equation is analogous to our force equation. Remember, yesterday we talked about how every quantity in rotation has a linear analog, right? Something to which it is analogous. Angular acceleration is analogous to linear acceleration. Force and torque are analogous to each other. And for that matter, mass and moment of inertia are analogous to each other, right? Mass represents resistance to linear motion. Moment of inertia represents resistance to angular motion. Okay, so the sum of the torques equals I alpha. All right, so what you have here then is, in the situation being described, two objects that are going to produce a torque on this meter stick, right? Where this one on the left here is going to produce a counterclockwise torque, and the one on the right here is going to produce a clockwise torque, which means that they would have to have different signs from each other. Okay, and if the meter stick is going to be in equilibrium, that means that we're saying that the sum of those two torques is going to have to add up to 0. All right, now what that's going to look like when we set it up is for each one of those torques, we're going to say the torque is that formula there, F cross R. The force, though, the weight of each one is different, and they are also at different distances, okay? So the torque produced by the 1 kilogram object hung on the left, I'm going to represent like this. I'm going to call that one M1 G, let's call it R1 for now. And then the torque produced by the object that I wrote in blue on the right side is going to be M2 G R2. All right, so force of gravity times radius minus force of gravity on the other one times the other radius is going to add up to, I didn't leave myself enough room, but 0 altogether, because they're saying that this is going to be placed in equilibrium. All right, so that means then that those two torques are equal to each other, right? A little bit of algebra later, I'll move the M2G R2 over to the other side, and we'll end up with M1G R1 equals M1G R2. All right, notice the factor of G is going to cancel out. And since, M2, I mean. Since we know one of those masses and then both of those radii, there's only one unknown here, which is the amount of mass that would have to hang like way over on the other side. So let's see, we've got 1 kilogram for mass 1. It is located at a distance of 10 centimeters from the pivot point. M2 is located at a distance of 0.9 meters from the pivot point, since the pivot point was placed right thereabouts, right? Okay, so it's 10 centimeters from one end, 90 centimeters from the other, which means that M2 is going to be 1/9, as it turns out. So 1/9 of a kilogram. Which is 111 grams, or 0.1 repeating kilograms. All right, now, we made a very important assumption here, which is that we were allowed to ignore the mass of the meter stick, right? We, in class, showed that like if you hold a meter stick by the end, it falls, because gravity pulls down right on the middle of the meter stick. Okay, so that means that the gravity acting on the meter stick exerts a torque as well. Okay, so if that is the case, then really we have 3 torques altogether. We have one counterclockwise torque from the 1 kilogram weight hung on the end. We have a clockwise torque due to the weight of the meter stick itself, and then another clockwise torque due to the weight that's hung on the end. Okay, so part B then is telling us that actually M2, the one on the end, only needs to be 90 grams instead of 111 to place the meter stick in equilibrium. Okay, so that means that we would then have to go and include the meter stick's weight in our list of torques, and then we can calculate things based on that. All right, fine. I will let you look at the work online for part B if you need to, but essentially you'd end up with, for that equation there, you'd end up with a third torque, right? You'd have like minus, because it's in the clockwise direction, right? Same direction as the M2. Another like M3G, okay, and then the radius that the center of mass of the meter stick is from the pivot point is 0.4. Right, the middle's at 0.5, pivot's at 0.1 from the end, so 0.4. Anyway, you can look at the work for that online if you need to. What I want to concern myself with in a lot of the rest of the video here is what do we do when it has fallen like a particular distance? Like how do we talk about the torque in that case? So when you have a falling object, not meaning like falling straight down, but rotating downwards, the torque is actually going to be a changing quantity. Whoops, that was supposed to be a straight line. Let's try that again. All right, that's straight enough. So let's say this represents the meter stick from the previous question, and again, we're going to put the pivot point, say, right there. Gravity acting on the middle of this object, we said, produces a torque, but as it falls, that torque is actually going to be constantly changing. So in this position shown, if I draw in my radial vector and my force vector, you can see in red there's my radial vector. My force vector I already drew in black. That's from the weight of the object. Those two vectors are perpendicular to each other. So that means that the torque, since it's F cross R, is going to be FR sine of 90, which just means that the torque would be mg times R. All right, so for the example that I picked, we could plug in the mass of the meter stick once we know that, and then the radius is away from there. All right, now, as it falls though, I said already the torque's going to change. The reason it changes is, let's draw it in a new orientation. There's our pivot point. Gravity still acts right at the middle, but, darn it, fat fingers, but there's our radial vector. The radial vector and the force vector are now at not 90 degrees anymore. Now, you have to pay close attention to which angle they give you and which angle you actually want. So sometimes they're not going to be so nice about this. So let's draw it a little bit carefully. The way that it's described in the problem is it says the meter stick has fallen, I think it says 30 degrees initially. All right, so it's fallen 30 degrees. So you might think, well, that means that my torque is just going to be FR sine theta, so probably FR sine of 30, right? Okay, well, it's not always the angle they give you, which is why I say you have to be careful. In this particular case, it will not be the angle they gave us, it's going to be the complementary angle. To understand why it's the complementary angle, let's draw our radial vector just a little bit longer, meaning I'll just continue it going. Here's my radial vector, right? All right, and here was my force vector. The angle between those two is what actually goes in for theta. So the angle between those two is actually this one, which you can see is the complementary angle to 30, so 60 degrees. So after this thing has fallen 30 degrees from the horizontal, the torque is going to be, instead of just mgr, it's going to be mgr sine of 60. So it's going to be less. All right. After it has fallen a little bit further, I'm going to have to draw this one a little bit smaller right there. It's fallen a little bit further, right? You can see that as it continues to fall, the force of gravity remains in the same direction, but my angle between my radial vector and my force vector is going to keep getting closer and closer to zero until eventually what we will have is the rod hanging straight down and my force vector and my radial vector are parallel. All right, so in that final orientation there, what we would say is the torque is going to equal 0. So as it falls, it experiences a changing torque, and that eventually decreases from a maximum value when it's horizontal to a minimum value of 0. All right, I hope that was helpful. If you need more examples to look at, go back and look at example 4, which is going to be very similar to the one that we did in class. So you can look at that worked out stuff in the answer key for the notes packet in the Google Drive. And that should help you with the first 3 parts of number 1 from your homework.